SwayamPrabha. Digital India. Educated India.
So, this particular module that is going to be module number 6, okay, we are going to discuss about bending of sheets. So, the bending of sheets, if you take, it is there in almost all sheet components that we see in day to day life. Okay. So, it could be as simple as a plate type of shape, or it could be a complex shape that we use in automotive industries, components, aerospace industries, okay, or in any other sectors. Okay. Bending is inevitable. Okay. So, analysis of bending of sheets, okay, which we are going to discuss in this module, is going to be maybe about 2 classes we are going to see. Okay. And some of the assumptions that we made earlier are valid for bending of sheets also, or we are going to introduce one more assumption, then we go ahead with our discussion. So, bending along a straight line is a very common form of sheet forming operations that we see in day to day life, and that is a simpler process to understand. Okay. So, of course, in for making components, it is not going to be straight line bending, it is going to be in any form. Okay. So, it is going to be any form. Okay. Suppose if you take a cup, a deep drawn cup, suppose we are making, okay, you will see that okay, it is bent in these locations, but you will see that the bending is not actually circular in nature, bending is going to be circular in nature. Okay. So, nevertheless, we are going to study mainly the bending along a straight line, which is easy for us to understand the theoretical part of the bending process. And bending along a straight line, we know this can be done in several ways. We can just bend it with the help of die punch setup. Okay, it could be done in the form of folding operation or a flanging operation in a special purpose machines. Okay, like in workshops we have bending machines available. Okay, so we can also bend sheets just holding it in a bench wise and then giving some displacement one of the edges it can bend. Okay, so there are several ways we can do bending operation, but of course the complexity of the machine depends on what kind of component you want to make. So, first of all, what we are going to discuss, we are going to introduce mainly the variables in bending a sheet. Okay, suppose if you take a sheet, aluminum sheet or steel sheet, what are the variables in bending that we discuss? For that, this schematic would be useful. Okay, so this is a bent sheet. Okay, so initially it could be as flat as like this. Okay, and now it is bent like this, isn't it? So, it is bent through an angle of theta that is given here. Theta is called as bent angle, and you need a tool setup for that, let us say, and it has to be bent with respect to one particular radius of curvature, let us say rho in the bent region. And then the right side diagram will tell you that this bending is possible in 2 ways. One is only moment, the other one is moment and tension, both. So, bending with stretching would be moment and tension, both are applied. In the other case, only moment can be applied. Okay, both are possible ways of bending a sheet along a straight line. Okay, so you will see that this T is called as a tension per unit width, we are saying. So, we are picking up a unit width which is applied at the mid surface of the sheet generally. Okay, you apply T at the mid surface of the sheet theoretically. So, practically how do you give this tension is by grabbing the sheet. Okay, you have to grab the sheet at these, let us say, locations, at these locations. Okay, so and then you are trying to push the sheet through a die cavity. Okay, something like that you can imagine. You are going to push the sheet through this die cavity, you can imagine. So you have a flat sheet, okay, and the flat sheet is grabbed at this end, and you are going to pull it with a punch, let us say a V punch or something like that, so that it becomes this kind of shape. Okay, so this is actually clamped here, and you are going to give displacement in this direction. So something like that is possible practically, okay, but theoretically you apply T at the mid thickness or mid surface of the sheet, and then moment is given in this fashion. So this is the tension per unit width, and then we get moment per unit width. M and T can be related. Okay, so these are the variables. So you have a bend angle theta, then rho radius of curvature, then tension and moment applied in the sheet. So now, as usual, what we are going to evaluate, first thing is strain. Like in the previous chapters, modules also, okay, we first evaluated strain from the new dimension with respect to the original dimension, and then we went ahead in calculating the other quantities when you deform a sheet. Similarly, here also we are going to first evaluate strain in bending. So again, I am going to take a simple case. For example, this is your sheet. This is your sheet you are taking with a thickness, let us say T. Okay, T or T by T naught, either way is fine. So it is going to be only thickness. Okay, so this is a total thickness is T. Okay, so let us say, for example, you consider a middle fiber, let us say C naught D naught, okay, a line which coincides with the mid thickness, and you can pick up any other line or a fiber which is y distance away from the mid thickness or C naught D naught, that is A naught B naught. So we are picking up two locations, one is C naught D naught, which is at the center middle, okay, and A naught B naught, which is at y distance from the middle, and you are picking up a section, okay, in the sheet with a original length of L naught, which I mentioned here as L naught. Okay, so you can imagine that this is T, which means that this is let us say T by 2, and let us say this is T by 2, you can say. So now this sheet is bent here, okay, so the bent sheet is drawn like this, and as usual you have a bend angle of theta with radius of curvature is rho, and you will see that the C naught D naught becomes CD, and you will see that A naught B naught is going to become AB. A naught is going to become AB. So how do you calculate strain in a simpler fashion? Okay, of course here we cannot put circle grid and evaluate strain. Okay, unlike in other deformation process where we put circle grids on the surface. Okay, here we are discussing about sheet bending, and we are looking at a section. That is why thickness is given here. That is why thickness is given here. Okay, so why we are showing a section when we have a bend? Okay, the bending is done with respect to this axis, isn't it? So why are we showing section? We will see in the next slide. But before that, anyway, we cannot put circle grids and evaluate because the sheet thickness would be about maybe 1.5 to 2 mm. So naturally we have to get it in a different way. So now we will say that while bending this particular sheet to this particular form, so C naught D naught becomes CD at the mid surface. That is number one. So now this L naught, okay, is going to become, let us say, LS when the sheet is bent with stretching. Okay, so we are going to consider a case, okay, where the sheet is bent, okay, not only with moment but also with tension. Both the tension and moment are available for us. So basically you are going to bend the sheet with stretching. Okay, so that means assuming the sheet is stretched during bending, okay, the original length L naught is going to become, let us say, LS, which is given by rho theta. So I am going to have this LS, okay, L naught is going to become, let us say, LS, and that will be given by rho into theta. Okay, this is with respect to the mid location C naught D naught. Now let us pick up a case which is a line or a fiber which is y distance away from C naught D naught, that is A naught B naught. Let us consider A naught B naught at a distance y from the mid thickness, and what will happen to L for that? That I am going to call it as L, which is nothing but I am going to add, this is rho, So, this point from here to here is rho, and from rho I am going to add this y part to it, assuming that this y remains same everywhere. Here also y, here also y, here also y, here also y. This is not going to change, which is same as that of the earlier y which you have taken before bending. Okay. So, I am just going to add rho plus y into theta. Okay. So, theta into rho plus y will give me my L, which is basically AB, okay, which is nothing but your AB. So, this can be simplified as rho theta into 1 plus y by rho, and why I am doing it is because I can replace this rho theta by Ls into 1 plus y by rho, Ls into 1 plus y by rho. So, this will give me L by Ls is equal to 1 plus y by rho, 1 plus y by rho. It will be useful for us now. So, you will see that now we need to find axial strain of the fiber AB, okay, axial strain of the fiber AB. So, this AB is like any fiber, okay, with respect to your mid thickness mid fiber CD, right. So, now we need to find strain at the fiber AB, okay. So, which I am going to call it as epsilon 1, which is nothing but my ln of L by L naught. So, AB is connected to L, and original distance length is anyway L naught for us. So, I am going to write ln of L by L naught as per our original definition, and this L by L naught can be written as L by Ls into Ls by L naught, okay. And if I take a logarithm, ln of L by L naught is nothing but ln of L by Ls plus ln of Ls by L naught, okay. So, ln of Ls by L naught will remain as it is here. I am writing here ln of Ls by L naught will remain as it is. I am going to write plus ln of L by Ls is nothing but 1 plus y by rho. So, ln of 1 plus y by rho I am writing. So, my axial strain of a fiber AB at any distance, let us say y, okay. So, this AB could be not necessarily in this location, it could be slightly above also, does not matter. So, which will be given by epsilon 1 is nothing but ln of Ls by L naught. What is Ls? Rho theta divided by L naught is original one plus ln of 1 plus y by rho, which I am going to call it as epsilon A plus epsilon B, and epsilon A is nothing but the strain in the mid surface. Whatever strain I have in the mid surface, that is epsilon A I am going to call, and I am going to add a component to that, that is called epsilon B, which is nothing but bending strain. The bending strain is given by ln of 1 plus y by rho, okay. So, this is epsilon A and this fellow is epsilon B. So, this ln of 1 plus y by rho can be approximated to y by rho, okay. Why? Because this y, you see that it is going to be pretty small, okay. So, we say this is t by 2, this y is going to be less than t by 2, okay. Suppose if the thickness is, let us say 2 mm, okay, then this y could be about 0.3 mm, y could be about only 0.3 mm, let us say. Okay. So, this 0.3 mm divided by this rho could be about 50 mm. This rho could be the radius of curvature on which you are bending the sheet could be about 50 mm. So, you can imagine that, let us say this is 0.3 mm and this is 50 mm, and then calculate ln of 1 plus y by rho, it will be almost same as that of your y by rho, okay. Or you can expand this, it is a series expansion, ln of 1 plus y by rho you can expand it, maybe you can take the first term only, which can be approximated to y by rho. So, you can say axial strain epsilon 1 as epsilon A plus epsilon B, where epsilon A is given by ln of Ls by L naught, which will give you strain in the mid surface, and epsilon B, which is nothing but y by rho. Directly you can write as y by rho, right. So, now if we plot this epsilon 1, okay, in this thickness direction, okay, in the thickness direction, if you want to plot this y, this epsilon 1, it will look like this. Okay. So, you will see that your epsilon 1 is nothing but epsilon A plus epsilon B, epsilon 1 is nothing but epsilon A plus epsilon B. The epsilon A is nothing but, what is epsilon A is ln of Ls by L naught, ln of Ls by L naught plus ln of 1 plus y by rho. So, I am just keeping it as y by rho, or ln of 1 plus y by rho also you can write. So, you will see that this is how the distribution is shown in the blue color. Okay. So, this is basically a section in the sheet, t by 2, this is a mid surface, let us say, okay, your middle surface, mid thickness, okay, and this is a strain distribution I have given here, okay, and then this blue color line will tell you the distribution along its thickness, and you will see that this blue color line is actually crossing 0 at a distance little below the neutral axis, little below the neutral axis. So, this also we need to know, neutral axis is nothing but this one, the axis at the center, you can say. Okay. So, to start with, okay, it is at the center. Now, you will see that this neutral axis is shifted towards the bottom side, where you generally expect some sort of compression, okay, and you will see that here it is going to be your 0 strain. Okay. So, which means in this equation, if you put y is equal to 0, if you put y is equal to 0, you will see at the mid location, okay, there will be some strain available in the material. That is what you are going to call it as epsilon A, and along with epsilon A, you are going to add epsilon B to get further strains above or below the section of the sheet. So, that is the meaning of epsilon A and B with respect to this particular strain distribution. So, if you have moment and tension, this is how the strain distribution looks like. Okay. With moment and tension is generally a little bit complex to understand, we will see that. Okay. But this is how strain distribution and bending can be calculated with respect to epsilon 1. So, epsilon 1 distribution in the thickness direction is given here. There are two components, epsilon A, which is nothing but the middle surface, your strain, and epsilon B is going to be your bending strain, which is additional with respect to epsilon A, and in this case at the mid location there is some strain epsilon A provided here, and y is equal to 0 if you put, this is what you will get as epsilon A. So, now this straight line bending can be taken as a plane strain bending process, can be taken as a plane strain bending process. Plane stress, it is still available with us. Along with that, we are going to include something called as a plane strain bending. So, we are going to say that if there is no constraint on either side of the bend and hence no deformation, the material in the bend deforms in plane strain. Okay. So, that means the strain parallel to the bend will be 0, parallel to the bend would be 0. Suppose with respect to this, if you take parallel to the bend means in this direction, if you pick up epsilon, it will not be, there will not be any strain in this direction when compared to your thickness and across the bend. When you compare thickness and across the bend, bending along the strain along the parallel to the bend would be 0. So, for an isotropic sheet, that is what we are discussing until now, we can take it as epsilon 1, which is going to be available, epsilon 2 as 0, but epsilon 3 would be equal to minus epsilon 1, because epsilon 1 plus 2 plus 3 would be equal to 0. So, this also means that your beta is going to be equal to 0, because it is plane strain bending, no? Epsilon 2 0. So, beta is nothing but epsilon 2 divided by epsilon 1, and epsilon 2 is 0. So, beta is going to be equal to 0 for plane strain bending. Okay. So, if beta is 0, alpha is going to be equal to 1 by 2, which we already derived using Levi-Mace's flow rule. The relationship between beta and alpha we have already seen. So, beta is equal to 0, we already seen plane strain deformation process, for which alpha is going to be equal to 1 by 2, which means sigma 1 will be available as usual, and sigma 2 would be equal to alpha into sigma 1, which is nothing but sigma 1 by 2, and sigma 3 is anyway 0, because we are going to take it as a plane stress process. Okay. So, now for this particular situation, say beta is equal to 0 and alpha is equal to half, we can relate sigma 1 to flow stress or effective stress and epsilon 1 to effective strain using our von Mises effective stress and effective strain equations. So, I hope we know this. Sigma bar is nothing but square root of 1 minus alpha plus alpha square into sigma 1. So, sigma 1 you will get as sigma bar divided by square root of 1 minus alpha plus alpha square. So, in that if you put alpha is equal to half, then you will get sigma 1 is equal to 2 by square root of 3 into sigma f, which is nothing but my plane strain flow stress, which I am going to call it as S. Okay. So, my plane strain flow stress, that means suppose if I am deforming a material in plane strain instead of uniaxial, then that can be related to my uniaxial flow stress by 2 by square root of 3 into sigma f, which is nothing but my plane strain flow stress. Similarly, I can also get epsilon 1 as a function of epsilon bar, okay, using my effective strain equation, which is nothing but my epsilon bar is nothing but square root of your 4 by 3 into 1 plus beta square into epsilon 1. So, that equation one can refer, and from there you can get epsilon 1 is equal to square root of 3 by 2 into epsilon bar by putting beta is equal to 0 in that equation. So, this is how you relate, you evaluate sigma 1, okay, and your epsilon 1 in the plane strain bending process, and we are going to use S here onwards rather than your sigma 1 directly. Okay, so, where S is nothing but your plane strain flow stress. So, we are going to say why your straight line bend can be assumed as a plane strain bending process, and while assuming that we are going to put epsilon 2 as 0, 1 is going to be there. This 1 epsilon 1 is nothing but this epsilon 1 only. Okay, we have got epsilon 1 here, the same epsilon 1, and epsilon 3, which is basically along the thickness direction, would be about minus epsilon 1. Okay. So, now we know how to calculate strain. So, now we need to develop a general equation for evaluating tension and moment during bending, for which I am going to use a simple equilibrium equation in this direction. This schematic will explain you that. So, it is the same schematic. So, I am going to have a bend sheet, I am going to have a bend sheet with rho as radius of curvature, and you can see T by 2 of thickness, and you can see that I am going to take an element which is at y distance from the mid thickness. The element is dy, okay, dimension. Okay. So, it has got a thickness of dy in the thickness direction, okay, and you will see that the force acting on that element is given by sigma 1 into dy into 1. Okay. So, this is basically for the unit section. So, force acting on a strip of thickness dy across a unit section is given by sigma 1 yd, sigma 1 dy into 1, sigma 1 into dy into 1, which is going to act in this particular section. So, in general I have given how tension is going to act in the sheet and moment is going to act in the sheet. Now, this tension in this section is given by T is nothing but you have to integrate this particular fellow. Okay, T is going to be minus T by 2 to T by 2 sigma 1 into dy. Okay. So, sigma 1, that is the now next thing what we are going to discuss, what will be sigma 1. Okay. So, for this tension we can get moment the same way, minus T by 2 to T by 2 sigma 1 dy into y into y, y dy basically. So, we are going to multiply that with this distance from the center, that is what is given here. So, in general you can write integral minus T by 2 T by 2 sigma 1 y dy. So, if we know sigma 1, then we can find out the tension and moment at this particular section when you bend a sheet. So, now how do you get the sigma? It depends on actually the material models that we are going to choose. That is what the next one is. Okay. So, we are going to assume some material model which relates sigma to epsilon. One thing which you have already seen is power law, that will be part of it. Other than that, there are few other models one can assume. Okay. So, by knowing the stress strain law, and by evaluating epsilon 1, okay, so or epsilon you can say, okay, one can get a sigma 1, and sigma 1 can also be plotted like your epsilon 1 in the thickness direction. Okay. And when we do that, we have to define something called as rho by T, that is called bend ratio. This rho by T is going to be useful for us, it is called bend ratio, where rho is your radius of curvature, same thing which you define, and T is the sheet thickness. This ratio is called rho by T. So, now there are few choices we have. The first one is elastic perfectly plastic model. Okay. So, in this elastic perfectly plastic model, the stress strain behavior is given in this diagram. It will be like this. So, elastic means you will have elastic part here, and then perfectly plastic means there is no hardening. Okay. So, your flow stress is going to vary in a horizontal way like this, okay, with respect to strain. Okay. So, you have a linear first variation and then a horizontal variation with respect to sigma and epsilon. Okay. So, the initial part is defined by slope, which is nothing but your E dash. The slope is actually E dash we are saying, and this height that or otherwise this value is nothing but my plane strain flow stress. My plane strain forces is nothing but probably this point is nothing but your yield strength you can say, but in plane strain deformation process like bending, which is what we are calling it as S. So, now with respect to this diagram, there are two parts in this. One is up to this strain corresponding to the end of elastic part and beyond that. So, there are two parts in this. There are two parts in this. So, if the stress is less than plane strain yield stress, yes, then okay, this equation can be defined as sigma 1 into E dash into epsilon 1, which is well known to us. Okay, sigma 1 in the initial part, that is in the initial part, in this particular part, we can say sigma 1 is nothing but E dash into epsilon 1. So, in the second part, for the strains greater than yield strain, if you go beyond this, we can simply say sigma 1 is nothing but S. We will simply say sigma 1 is nothing but S. So, in this part, it is nothing but sigma 1 is equal to E dash into epsilon 1, whereas in this part, it is nothing but sigma 1 is equal to S, we can say. There are two parts here which will be useful for us. Okay. And what is this E dash? Generally we say E, but here we call it as E dash. E is nothing but your modulus of elasticity, but E dash here is nothing but modulus of elasticity in plane strain. Okay. Not in uniaxial, but in plane strain mode of deformation. Okay. And this E dash can be found out from this particular equation. E dash nothing but E by 1 minus nu square. Here E is nothing but uniaxial Young's modulus and nu is your Poisson's ratio. So, both are given, we can get E dash can be substituted here, and epsilon 1 can be evaluated from the previous distribution at any distance, let us say y from the mid surface, you can get sigma 1 there. You can get sigma 1 in that location. So, if E is known and nu Poisson's ratio is known, you can get E dash, put it in this equation, epsilon 1 can be found out from the previous distribution that we have already shown, and you will get the sigma 1 at any distance from the mid surface. For example, at y distance, you can get sigma 1. Okay. So, now how is that going to look like? We will see in due course, but since these are some material models, we are going to see another model, it is called as rigid perfectly plastic model. Rigid perfectly plastic model. So, in rigid perfectly plastic model, as the name suggests, since we say it is rigid, we do not bother about elastic part, which means it is neglected. Okay. And strain hardening is also neglected in this, and strain hardening is also neglected in this. So, you get a stress strain graph in this fashion. So, this S is nothing but your plane strain flow stress, and this is how you define your stress strain behavior for a rigid perfectly plastic model. Strain hardening model is a conventional one that we know, we have already known about this. This strain hardening model is a perfect one that we look into it, which will take care of the hardening that you have in the bending process, and this is given by sigma 1 versus epsilon 1 is nothing but like this. It is going to have a very small elastic part and then a large strain hardening part, which is modeled by sigma 1 is equal to k dash epsilon 1 power n. This k dash is also actually like k only. Okay, only thing is we are writing k dash because it is a plane strain forming process. Okay. So, sigma 1 is nothing but k dash into epsilon 1 power n, and n has the usual definition, nothing but the strain hardening exponent. So, we can have several other models. We already seen like you can have with pre-strain. Okay, you can also have sigma naught into the equation. Okay, so all are possible, but then we will restrict to only these three equations. So, now we are going to pick up one important case called bending without tension, and we are going to do some analysis. That is the first thing. So, whatever we are going to discuss is basically bending without tension. So, only moment. Okay. So, only moment is available for us. So, we can say that sheet is bent without tension, but with moment only. Okay. So, what will happen? The neutral axis will be at the mid thickness. The neutral axis will be at the mid thickness. So, when we say there is no tension and only moment, okay, what will happen to epsilon 1? In this case, epsilon 1 is nothing but epsilon A plus epsilon B, isn't it? So, we say that in this case, since the neutral axis will be at the mid thickness, okay, this fellow will go off, epsilon A will become 0, this fellow will go off. So, epsilon 1 will be approximated to epsilon B directly, epsilon 1 will be approximated to epsilon B directly, so that when you put epsilon B as y by rho, epsilon B is nothing but y by rho, if you put y is equal to 0, epsilon 1 will also become 0, which means, so your strain at the mid location is nothing but 0. So, that is what we are going to have for this strain distribution. Now, what will be the stress distribution? For that, how we are going to assume some material model and we get that. That is the whole objective of this particular section. So, we are going to take the first case, which is nothing but elastic bending, and for this case, so the stress strain behavior will look like this. Okay. So, you will see that y axis is sigma 1, x axis epsilon 1, and the initial part is E dash, and then we are going to have a non-strain hardening region with a yield strength of, let us say, plane strain yield strength of S. And for this case, it is very straightforward. You get a strain distribution in this fashion. Okay. So, T by 2, it is going to be 0 at the mid location. Why? Because the neutral axis will stay at the mid thickness. Okay. And that is because epsilon A is 0. And that is because epsilon A is 0. So, for this, you have to get a stress distribution. That is what our aim here is. So, here very simple is basically sigma 1 is nothing but E dash into epsilon 1, because bending is only elastic. So, you are going to use equation relevant to the first part. We already discussed just now that sigma 1 is nothing but E dash into epsilon 1, where E dash is nothing but your plane strain elastic modulus. Okay. And since epsilon 1 distribution is known to you, you can get sigma 1 distribution as this particular figure. The strain distribution, the corresponding stress distribution is given in these two figures. If you assume this particular model to describe the bending process, sigma 1 is equal to E dash into epsilon 1. Okay. So, now if you want to get a stress at any distance, let us say y, any distance, let us say y from the neutral axis, let us say, then what is that? Then sigma 1 is nothing but E dash into epsilon 1. This epsilon 1 has got two parts, epsilon A plus epsilon B, we said this fellow will go off. Okay. Then sigma 1 is equal to E dash into epsilon B, E dash into y by rho. I can write sigma 1 by sigma 1 divided by y would be equal to E dash by rho. This is an important equation for us. E dash by rho is equal to sigma 1 by y. You will use this relationship in due course. So, now if this is the case, how do we get moment in the section? Okay, because we need to have moment. No, this moment is what is responsible for bending. So, we need to get that moment, and general equation we already discussed, integral minus T by 2 sigma 1 y dy, and y dy will remain. I was hinting you that what will happen to the sigma 1 in this particular case. Sigma 1 is nothing but E dash into y by rho, which we just now discussed. Okay. And you will see that E dash by rho will come out because they are constants. Okay. And minus T by 2 you can call it, you can take it as 0 to T by 2 into 2 because it is symmetric in nature. Okay. So, 2 into E dash by rho integral 0 to T by 2 y square dy. So, you can integrate it. Okay. Put your limits. Finally, you will see that you will get E dash by rho into T cube by 12, which can be written as this T cube by 12 is nothing but my I, okay, with unit width, considering unit width, that is the thing. Okay. So, I can write m by I, this m by this I is equal to E dash by rho, which will be obtained from this, which will also be equal to my sigma 1 by y, which is obtained from this equation, where I is equal to T cube by 12 for unit width. It is second moment of area for unit width. Okay. And 1 by rho we call it as a radius of curvature. So, we need to note down this 1 by rho is the curvature, 1 by rho is the curvature here. So, m by I is equal to sigma 1 by y is equal to E dash by rho is the equation that we get, and moment for this particular case is given by E dash by rho into T cube by 12. So, E dash can be evaluated from E and nu, and rho is given, T is given, sheet thickness is given, then you can get a moment for that particular bending operation. So, we can also evaluate this limit of elastic bending. We can also evaluate this limit of elastic bending by putting some conditions what we see during bending. So, the limit of elastic bending, that means limit of elastic bending means how long are you going to be there within this zone? How long are you going to be there within this zone? Okay, can be obtained by this particular discussion. The limit of elastic bending is when the outer fiber at y is equal to T by 2. Y is equal to T by 2 is this particular one. Y is equal to, this is number our y, no, this is our y. Y is equal to T by 2 means this particular surface. This particular surface. Okay. Y is equal to T by 2. If you put that condition y is equal to T by 2, you will reach this particular surface, the upper surface. The upper surface is generally undergoing tension as compared to the lower surface, that we understand while we bend. Okay. So, reaches a plane strain yield stress, correct. So, whenever you are bending it, okay, the uppermost fiber which is at y is equal to T by 2 will reach a plane strain yield stress, right, if that is a limiting case. So, it should be as long as it is within this region, no problem. The moment it reaches S, where at y is equal to t by 2, okay, at the upper surface, we call it as a limit of elastic bending. So what do we do now? This moment equation is sigma 1 by y into t cube by 12, which you already derived. Moment is equal to sigma 1 by y into I, which is nothing but t cube by 12, right. So moment m is equal to I sigma 1 by y, so I t cube by 12 into sigma 1 by y, correct, which is what I have given here. So what I am going to do is, I am going to substitute sigma 1, when it becomes yes, y becomes t by 2. That means when y becomes t by 2, sigma 1 becomes yes for limiting case. So I am going to say that substitute this. So 2 will come in the numerator, so 2s by t into t cube by 12, it will be st square by 6. Since it is a limiting elastic moment, I am going to call this as me. This will be called as me. So me is given by st square by 6. So the limiting elastic moment, okay, so given a sheet thickness, given a yield strength of the material, you can get plane strain yield stress or flow stress, you will get me, limiting elastic moment. When you reach this particular moment, what will be the radius of, what will be the curvature? 1 by rho. That will be given by this equation. So 1 by rho is nothing but again the same thing. 1 by rho is nothing but your sigma 1 divided by E dash y. Sigma 1 divided by E dash y. Okay. So this y is nothing but my t by 2. At t by 2, this fellow will become s. So it is nothing but 2s divided by E dash t. So when m becomes me, 1 by rho would be 2s by E dash t, okay, which can be represented in a moment curvature diagram. Like we have a stress strain diagram, we can also have moment 1 by rho. If you plot it, you will get a straight line, and you will see that this particular height is nothing but your elastic moment height, me, which is nothing but st square by 6, which you already evaluated, and this 2s by E dash t is nothing but your 1 by rho, okay, when you reach me, that is 2s by E dash t. Both are represented in this particular diagram. So this is moment curvature diagram for this particular case. So these results will be useful for us in the analysis that we will discuss in the next section. Now we will go to rigid perfectly plastic bending. So where we the model is very simple. Your sigma 1 would be equal to s, okay. So there is no elastic part, there is no hardening also, and it is pretty straightforward. The sigma 1 is equal to s will give you a stress distribution like this, okay. So you will have like step type of thing, okay. So this would be your s value, okay, and there will be a transit at the middle, and you will have another variation on this side of the bent region, okay. So now the point here is, since there is no elastic part here, the moment itself is actually fully plastic moment. Like in the previous case we say me, here we are going to call it as mp, which is nothing but fully plastic moment, because there is only one case, that is your plastic moment only, because there is only, because it is rigid perfectly plastic, no. So there is no elastic part. So directly we will write mp, which is given by, directly I am writing 2 into 0 to t by 2 sigma 1 y dy, that is actual one. Sigma 1 is nothing but s, so I am going to put s y dy. S is actually anyway material property is a constant, 2s y square by 2, 0 to t by 2, you integrate it, put limits, finally you will get st square by 4. This st square by 4 can be drawn in a moment curvature diagram as this way. It is going to be a horizontal line similar to what you see in stress strain graph, and this height is st square by 4. Okay. So me, the previous one, is nothing but st square by 6, and mp here what we are going to discuss nothing but st square by 4. These two are important ones we need to remember. The next case is a general case, which is what is important for us. You are bending a strain hardening sheet, okay, which means somehow you have to bring in your strain hardening part of into the equation. So that's why we are saying it is sigma 1, sigma is equal to k epsilon power n, same power law, only thing is sigma 1 is equal to k dash epsilon 1 power n we are keeping, okay, and this is approximated to, okay, sigma 1 k dash epsilon 1 power n is approximated to, k dash will remain as it is, your epsilon 1, there is no epsilon a, so it is epsilon b only, so epsilon b is y by rho, k dash into y by rho power n would be your stress distribution that you are going to get, and the stress distribution to some extent schematically it can be drawn in this fashion. So, T by 2, this will not come. Okay. So, you are going to say that it is going to vary in this fashion and it is going to come down like this. This would be your sigma 1 distribution for a general material model like sigma 1 is equal to k epsilon power n. Okay. So, now if you want to evaluate moment for this, okay, so it is the same thing. Okay. So, you will see that your moment is nothing but I am going to write 2 times 0 to T by 2 sigma 1 y dy, right, where sigma 1 is nothing but here k dash y by rho power n. Okay. This is k dash y by rho power n you can keep. Okay. So, what will happen now? So, 2 k dash y by rho power n will be there outside. So, 0 to T by 2 will remain, and then there will be a component of yn. So, y is already there. So, y 1 plus n into dy. So, you can integrate it, apply your limits. Finally, you will see that it will be equation is going to be m by I n, nothing but sigma 1 by yn is equal to k dash 1 by rho power n. Okay, where I n is same as that of your I t cube by 12 that we have seen, but here it is very general in nature. I n is nothing but this entire thing t power n plus 2 divided by n plus 2 into 2 power n plus 1. Okay. And if you want to draw a graph between m and 1 by rho, okay, it will be something like this. It will be a smooth curve. It will be something like this. M versus 1 by rho would be similar to what you see in a stress strain graph. Okay. And this is a general equation taking strain hardening into consideration. And all our known values, moment is moment per unit width, sigma 1 is the principal stress, and y means it is any distance, okay, from the neutral axis. K dash is nothing but an equivalent of strength coefficient, 1 by rho is a curvature, and n is the strain hardening exponent that you get. So, if you put 2 cases here, okay, for example, if you put n is equal to 1. So, if you put n is equal to 1, okay, so you will see that this sigma is equal to, we say k epsilon power n, isn't it? So, sigma n is equal to 1, it is like k dash will become e dash, okay, like n is equal to 1 if you put here. So, it is nothing but sigma 1 k dash epsilon 1, but which is nothing but k dash nothing but e dash only, which you have defined before, So, that is what I have said here, k dash is nothing but e dash. Then we can directly write from this equation m by I is nothing but sigma 1 by y is equal to e dash into 1 by rho. From this you can directly write this. When n is equal to 1, if you put, you get this. So, you can also put n is equal to 1. So, you can put n is equal to 0, it will go to the other case, the other extreme case. When you put n is equal to 0 here, you will get n is equal to 0, you can put, so n is equal to 0 here means it is t square divided by 0 4, t square by 4 you will get, okay. And so, your n is equal to 0 means, yeah, so your k dash will be straight away it will be nothing but yes, okay, and then you can, which means that you will have only MP, okay. So, it is k epsilon power n is 0 means straight away you can say your sigma 1 is nothing but k dash, here in this case yes only, s is nothing but k dash, okay, and it is going to be MP only because it is a fully plastic moment. And if you see that MP can be calculated from the previous equation, okay, from this equation if you put MP, okay, it is going to be m is nothing but In into sigma 1 divided by yn. So, In is nothing but t square by 4. So, t square by 4 sigma 1 will become s in this case, okay. So, then y power 0 it will vanish. So, s into t square by 4, will come, okay. These two are two extreme cases when you have n. So, this one will actually lead to the case which we already discussed. This one will, when you put n is equal to 0, this one will lead to a case which we already discussed. This will also lead to the previous case what we already discussed. So, this way one can get in a bending without tension, okay, one can get if you know the strain distribution, the simpler case. Why? Because this fellow goes off, Okay, that is why we are picking up this particular case. In this case, if you know epsilon 1, you can get a sigma 1 by assuming different material laws. Okay, one is this first one, next one is sigma 1 is equal to S, next one is with strain hardening, and in each case you are going to have moment curvature diagram that is going to be different here. Okay, stress distribution is also different. Okay, and you will see that your moment curvature diagram is also going to be different. So now, before we go ahead and discuss another small section in this particular module, let us do one small problem with whatever we discussed until now. The question is given here, a 2 mm thick aluminum sheet, okay, has a constant flow stress of 120 megapascal. Okay. So, which means that it says constant flow stress, which means that you have to take it as a uniaxial flow stress, okay, as 120 megapascal, it is not going to change with strain. Okay, it is a constant one. Now, the question is, determine the moment per unit width to bend the sheet to a limiting elastic state. Okay, that means first question is you need to get ME. First one, you need to get a moment per unit width to bend the sheet to limiting elastic state, that is ME. What is the radius of curvature 1 by rho at this particular stage? So, when M becomes ME, what will be the radius of curvature 1 by rho? Determine the fully plastic moment, the sheet is bent further. Okay, so you are not stopping with the limiting case, you are bending further. Okay, what will be the your fully plastic moment, that is MP. Okay, two cases, two values are given. One is Young's modulus, other one is Poisson's ratio. These are known to us. Aluminum sheet has got Young's modulus of about 70 GPa and Poisson's ratio is about 0.3. So, we need to know ME. So, it is understood. ME is already derived, which is nothing but ST square by 6, which we already derived as ST square by 6. We put a condition, no? So, when y is equal to T by 2, your sigma 1 will become S, isn't it? So, if you substitute in this particular situation, you will get ME is equal to ST square by 6. Now, thickness is given as 2 mm, only thing is you have to get S. S is nothing but plane strain flow stress, which you already got a relationship. S is equal to 2 by square root of 3 into sigma F. In the second section we have seen this particular one. Sigma 1 is equal to 2 by square root of 3 into sigma F, right. The sigma F is actually given. When you say simply flow stress, we can take it as sigma F. So, 2 by square root of 3 into 120, if you calculate it, it will give you about 138.6 megapascal. Okay. So, S has been found out. So, what you can do is like you can substitute this S in this equation. So, 138.6. Okay. So, you want to keep consistent units, that you have to be careful. Okay. So, 138.6 into 10 power 6 into T square, 2 into 10 power minus 3 square divided by 6, which will give you your elastic moment per unit weight. 92.3 is a value that is given. So, this has been found out now. So, now next one is we need to get 1 by rho at this particular stage. That is, so you want to get this, then we already derived this equation E dash into T by 2S, that we already derived. E dash into T by 2S. It is radius of curvature. So, it is radius of curvature. So, it is rho. Okay, rho E, because it is a limiting case. No, it is rho E. So, rho E is nothing but E dash T by 2S. No. So, where is it? Yeah. So, rho E is nothing but E dash T by 2S. E dash T by 2S. This also we derived already. Okay. So, T is given, S has been found out already, E dash have to be found out. So, E dash nothing but E by 1 minus nu square, E is 70, 1 minus 0.3, keep consistent units here. So, you will get E dash as 76.9 GPa. It is slightly larger than what you see in your uniaxial Young's modulus. 76.9, here you can see 70. So, that 76.9 you can substitute, appropriate unit conversion you have to follow into thickness is this one divided by 2 into your S is already 138.6, which is given here, which will give you rho E as 0.56 meter. You can convert that into millimeter also if you want. Okay. So, second one is also found out. Okay. Next one is basically if you further deform it to fully plastic moment, what will be the value? So, that is also found out. MP is nothing but ST square by 4, which we already know. So, either you substitute this S, T and then get it. Otherwise, what you can do is you can relate that to ME. Okay. So, we can also see MP by ME is how much. So, MP is nothing but St square by 4 divided by Me is nothing but St square by 6. You will see that this is Mp by Me is 3 by 2. This fellow will go 6 by 4, which is nothing but 3 by 2. So, I can get Mp is nothing but 3 by 2 into Me. I can get is Mp is equal to 3 by 2 into Me. That way I can get, so Me is already known to me, 92.3, you can substitute here, you will get Mp as 138.5. Okay. Or you can directly get Mp as directly St square by 4. You can substitute all the values here, you will get the same value. So, S is given here, T is already given as 2 mm, use consistent units, finally you will get Mp. Either way it is fine. So, in this way we can find out moment per unit width for the limiting case or the radius of curvature at this stage and the plastic moment with whatever we have discussed until now. These derivations are already done. So, now let us go to one important section. We will not discuss this fully today, but then rather we will discuss certain things conceptually. Elastic loading and spring back. This spring back is going to be very important for us in sheet metal forming. This is actually a defect. Okay. So, suppose if you consider a thin sheet like this and you want to create a hat type of structure. I want to create a channel like this, hat type of structure you can imagine. Okay. So, once I unload the material, it may so happen that this fellow hat will become something like this. I am just drawing schematic, it can become something like this. This is your initial one, okay. This is a formed one, okay, and after unloading your sheet can become like this. This dimensional change which you are looking at, no, here and here, this is actually called as a spring back. This dimensional change, this angular change is called as a spring back. So, you need to have a flat flange, but here you can see some angle is created. This wall also can have some angular displacement, which is what you are calling it as a spring back. Basically, dimensional change in the sheet once you unload the material is what we refer as a spring back. So, why this spring back happens can be understood from these three schematics. Okay. So, you will see the first one, sheet is bent, okay, and you will see that this is your neutral axis at the mid region, that is your pink color line, and above that you will see that if you take any point or any element, it will be pulled, that is it will be in tensile mode of deformation, and at the inside location you will see the elements will be compressed. Suppose this will be compressed, this will be fully tensile mode of deformation. Okay. And since we are discussing anyway bending without tension, you will have the stress and stress distribution, strain and stress distribution to be 0 at the mid surface. And you are going to pick up, let us say, a point A, okay, point A here, okay, and the point A has got a tensile stress like this, which can be represented in the stress strain diagram like this. Suppose a corresponding stress strain diagram of the material is given here. You can see usual things like you have yield strength, then you have UTS, then you have F, and this A point, this A situation is measured here. This A situation is measured here. That means you are bending a sheet at one particular location above the neutral axis. You can see a tensile stress, let us say A. The A is in between yield strength and UTS, which is mentioned here. Okay. And that means when you say strain as and stress as 0 at the mid surface, it means you are starting from here. It means you are starting from here and you are moving towards A, and you are moving towards A, let us say, in this direction, which means you are going to cross yield strength and you are going to reach A, okay, and then you are going to go further. That is the meaning. Okay. So, moving from this point to A is nothing but you are going along this direction, reach the yield strength and then cross that and go to A. That is the meaning. What does it mean? That means that there is a small region above and below the neutral axis, which is actually in the elastic part, and above that and below that band there will be a plastically deforming zone, which is described by the strain hardening part. That is what I represented in this particular diagram. So, you will see that with respect to neutral axis, there is one small red color hatched region. This region is called as elastic zone, which describes this particular part. With respect to stress strain curve, it describes the elastic part of the stress strain diagram, and above that you will have a zone deforming plastically because of tension, and below that, this lower boundary, you can have a region which is deformed plastically because of compression. Okay, that means above neutral axis, below neutral axis, there is a small band of elastic deformation, and beyond that you will see that you will have plastic deformation because of tension and compression. So now this is the situation we have. So we say spring back occurs because of variation in the bending stresses across the thickness from inner to neutral axis to now outer surface. Okay, from inner to neutral axis to outer surface. Okay, there will be variation in bending stresses which you already calculated sigma 1, and we are saying that is the reason for spring back. And we are saying that the zone above neutral axis deformed plastically because of tension, and zone below neutral axis deformed due to compression. That also we know. The stress at any point A in the tensile stress zone should be less than UTS. We are saying that this A point should be less than UTS. Otherwise, what will happen if A reaches UTS means a crack can develop at this location, at the upper surface. A crack. Otherwise, the outer surface will crack. So now what we are saying is this particular one, the metal region near the neutral axis is stressed below the elastic limit. Okay, so still it is in elastic deformation. Okay, that is near the neutral axis. That is this particular zone. Okay, this elastic deformation is a narrow band on both sides of the neutral axis. That is what I have mentioned here. So now what will happen? Okay, so you will see that during stamping and after stamping. So you want the sheet to be bent like this, but after stamping, after removing load, it can become like this. So this is what we said as a spring back. So upon load removal, the elastic band, okay, which is just above and below the neutral axis, tries to return to the original flat sheet. Correct. That is the purpose of elastic deformation. It will try to recover, right? Okay, it will try to return to the original flat sheet, but it cannot do that due to restriction given by the plastic deforming zone. So what we are saying is this red color portion, which is representing elastic part, will try to recover, okay, which is equivalent to change in dimensions, but the plastic part which is outside and below this neutral axis, below this region, elastic region, will not allow it to come back fully. Okay, but there will be some small change in the dimension, which is what we are going to represent as a spring back. But some return occurs as the elastic and plastic zones reach an equilibrium condition. This return is termed as a spring back. So full recovery, full dimension change is not possible because you already given some partial plastic deformation to it. Okay, and that actually suppresses the release of elastic part. Okay, but still, okay, some dimensional changes occur, which is what we call it as spring back. And if you want to represent it using a stress strain diagram, this we already discussed. So this is a typical stress strain diagram of any material. So you have yield strength, then you have a strain hardening portion, then after that you have a decrease in stress strain curve. Now, so in the loading part means your sigma will keep on increasing. Let us say when you are trying to unload the material, we know that the unloading curve is going to be this one, which is going to be parallel to the elastic part and will reach this particular point. Okay, and from this to this, if you measure, this would be a cause of permanent deformation. The remaining one is actually responsible for spring back. This part is actually responsible for spring back. So schematically, this way we can explain what is spring back with respect to stress strain graph. So there is a loading part in the stress strain graph, there is an unloading part, the remaining one, which is what is responsible for spring back. So now, with respect to this diagram, one can tell some important properties which can affect the spring back. For example, strength. Okay, strength of the material. Okay, so for that I have given some simple example here. Suppose this is your sigma versus epsilon graph. Okay, so you will see that this black color portion is nothing but your high strength material, and the red color one is nothing but your low strength material. You will see that at the same strain you deform it and then try to unload it. The red color one, low strength, will try to unload it in this path, whereas the blue one will be in this path, and you will see this a change in the spring back. So high strength actually has more change in strain, which is responsible for more spring back. So larger the strength, spring back would be larger. But at the same time, if you change the elastic modulus, here these two materials have got the same elastic modulus. Suppose elastic modulus is like this. okay, and then you are deforming it to the same strain, and then you are unloading it. Your unloading curve would be something like this, which will be parallel to this. Now you will see that this change is going to be much larger as compared to these two, which means that if you change if you increase the elastic modulus, there are chances that spring back will reduce. If you increase that means if you decrease the slope, okay, you will see that your spring back is more. That means larger elastic modulus will lead to lesser spring backs. Often this sigma ys divided by E, this ratio becomes very important, because the sigma ys can be controlled individually in this fashion, and E can be controlled in this fashion to control spring back, but both these values are in a way related to your elastic part of deformation, which is what is responsible for spring back. Often this ratio is used. We will also derive one equation in that you will see instead of course we say sigma ys by E, actually it is actually going to be S by E dash, S by E dash, the corresponding one in plane strain bending, no, that is nothing but S by E dash. This ratio becomes important for us. So one can control spring back by controlling the strength and Young's modulus of the material, and moreover you can also control spring back by this particular ratio called as R by T, where R is your the radius of the tool at which you bend the sheet, and T is the sheet thickness. Basically R determines whether it is sharp bend or blunt one, or a blunt one. So suppose if you take a sharp bend, what will happen? It will concentrate stress more in the gradual bend, okay, so resulting in more plastic strain. So smaller R by T ratios will result in less spring back. So what we are saying is, if the radius is small, you put lot of plastic deformation to it, plastic strain to it, which can suppress the elastic part. So there are chances that you will have lesser spring back, and if you increase your radius to a larger value, then it is going to be opposite to that. Okay. So other than this, spring back can be controlled by tool design also. The general rule is you overbend it. Okay, suppose like in this particular case, what we do is, suppose this is a flat sheet and you want to bend it to this one actually. So instead of that, what you do is you little bit bent inward, so that when you release it, it can become straight. In that way one can, this is basically called as overbending. That is one way to control it. There are a few other ways also that people control. So one can deform material at higher working temperatures. Okay, in that way also one can see how spring back can be controlled. Okay, die design can be modified to take care of spring back. There are several lots of work people have done to take care of your spring back, how to control spring back. So now if you want to evaluate some theoretical model, okay, let us say you want to develop some theoretical model for spring back, okay, so a simpler way to evaluate theoretical model for to estimate, to derive a theoretical model for spring back will be discussed here. And then of course we are going to first take a case of moment without tension. Okay, so moment without tension, we are not going to derive it now, we will just introduce this here now. So you have a sheet, as usual you can see I have just shown a thin line which is a sheet. This is your, let us say, sheet, no tension. Okay, so only moment is applied as shown in this figure, and there is a theta bend angle, okay, and radius of curvature is rho is known, and this L is actually the length of the mid surface, which is already known to us. So now this is a bent sheet. Okay, there is a flat sheet and you are bending it, this is a situation. Now you are releasing the load, which is an unbent sheet, this will be the situation. Okay, this theta will become theta plus theta naught, okay, and rho would become rho plus delta rho. So theta would become theta plus delta theta, and rho would become rho plus delta rho. So since there is no tension, only moment is given, we can say that this length will remain same. The length of the mid location, the mid surface, okay, or the neutral axis will remain same. Okay, it is not going to change. It is not going to change. When the sheet is bent and released by removing moment, there will be a change in curvature and bend angle. Theta becomes theta plus delta theta, rho becomes rho plus delta rho. The length of the mid surface L is given by rho theta. L is given by rho theta. This we already discussed in the first slide. this length we are saying will remain unchanged during unloading as the stress and strain at the mid surface is 0. Why? Because it is moment without tension. It is moment without tension. Okay. So, because of that the length will remain same, and then from this equation we can directly write this theta will be equal to L into 1 by rho. If you differentiate this equation, you will get del theta by theta is nothing but del 1 by rho divided by 1 by rho. Okay. So, where del theta is a change in angle due to this dimensional change called spring back. Okay. There will be a corresponding del 1 by rho. Okay. And if you can normalize it with respect to original theta and original 1 by rho, you can, this equation is valid. Okay. So, it is like either you calculate delta theta or del 1 by rho to quantify spring back. Either you calculate delta theta or del 1 by rho in a way to quantify spring back or to estimate spring back. When you have moment without tension. When you have moment without tension. Okay. So, we stop here, we will continue this.